Here are a couple pictures of Jean-Baptiste Biot and Félix Savart. So the law of Biot-Savart looks very similar to Coulomb's law. They both represent inverse squared laws. Let's try to make the comparison here. Coulomb's law says there's a little bit of electric field at any distance from some little bit of electric charge. So if this is a tiny positive charge and the point in question is some distance r away from it, then, and there's a vector 1 unit long called r hat, then the little bit of electric field at this point in question is equal to 1 over 4 pi epsilon naught times dq over r squared. And if we multiply that by r hat, this becomes a vector quantity. And then the law of Biot-Savart for a charge in motion, as we just saw, dB is equal to mu naught over 4 pi. Okay, so instead of 1 over 4 pi epsilon naught, mu naught over 4 pi. But then there's still an inverse squared law, and there's still an r hat. The only difference is now it's not just the amount of charge, it's the amount of charge and how fast it's going. And because velocity is a vector, then I have to decide whether velocity and r hat are cross product or dot product, and it's cross product. So seems like there's a pretty big similarity between these two formulas. The other version of law of Biot-Savart for a current mu naught over 4 pi, inverse squared law, cross product with r hat, but instead of dq and v, it's I and ds. So I think we used this formula back in our study of electrostatics whenever we were using a method we referred to as the brute force approach. So the brute force approach went something like this. Maybe I have not just a single charge that I want to find the electric field for, but I have a distribution of charge. And it could be a distribution of charge in a shape like this. Maybe we've got a charged rod that's been bent into a semicircle. And we want to find what's the overall strength of the electric field at the origin. So we take the charged rod and we divide it up into little bits of charge. Now if the whole bent rod has a charge of capital Q, then all these little bits have a charge of dq, and they're at a distance of r away from the point in question. And so if dq is 1 over 4 pi epsilon naught dq, if dE is 1 over 4 pi epsilon naught dq over r squared times r hat, then the total electric field is the summation of all the little bits of electric field. By the way, this little bit of charge right here makes an electric field vector that points that way, but this little bit of charge over here makes an electric field that points in that direction. The overall net electric field is just going to be a field that points straight down. So to sum everything up, we're going to take 1 over 4 pi epsilon naught times the integral of dq over r squared, right? So that's what we call the brute force approach. Now, there's another approach known as Gauss's law. But there's no way that we could use Gauss's law with a problem like this because there's no Gaussian surface that we can draw that would make Gauss's law an easier approach than the brute force method. So similarly, when it comes to finding magnetic fields, there's a brute force approach. And then there's another method. It's not Gauss's law, it's called Ampere's law. Now, if you remember, Gauss's law is the one that said the total electric flux, right? The integral around a closed surface of the dot product of electric field and area vector is equal to 1 over epsilon naught times the amount of charge inside of your Gaussian surface. Ampere's law is kind of similar. instead of a closed surface, what we have is a closed loop integral. And we take the product not of electric field, but of magnetic field, and not with area, but with distance. And that's equal to mu naught, as opposed to 1 over epsilon naught, times the amount of current that's enclosed by whatever loop is represented by ds. But we're not there yet. We're not ready for Ampere's law. We want to apply the brute force method, and the brute force method is the law of Biot-Savart. And we'll probably stick to this form of the law of Biot-Savart. dB is equal to mu naught over 4 pi I ds over r squared cross r hat. And so we'll try to apply the law of Biot-Savart to a few different cases. One of them would be find the magnetic field at some point P near a long straight wire. Another case where we could apply the brute force method would be to find the magnetic field. If we take the wire and bend it into a circular loop, then we'll ask, what's the magnetic field at the center of that loop? We could say we take that exact same loop of wire, turn it on its side, and say, what's the magnetic field at this point P? What else could we do? Oh, I guess we could take that loop of wire and wind it around many times, and then get a second one, and also wind it around many times, run a current into both of those loops, and ask the question, what's the magnetic field at the midpoint between these two loops? Actually, that arrangement, if the radius of the loops is r, and the distance between them is also r, then we refer to that arrangement as a Helmholtz coil. So we'll apply the law of Biot-Savart to find the magnetic field at the center of a Helmholtz coil. Where else will we use the law of Biot-Savart? Now, there's maybe a couple examples. Then we'll get into some other situations where it might be easier to use Ampere's law. For example, we might be able to use Ampere's law as well as the law of Biot-Savart in case number 1, but there's no way we could apply Ampere's law in cases 2, 3, or 4. However, we could probably use Ampere's law to find the magnetic field on the inside of a solenoid. When you take the solenoid and wrap it around on itself, then you can form like a donut shape winding of wire, and that's referred to as a toroid. And those are both examples where we might use Ampere's law. But again, I'm getting ahead of myself. We want to stick to the law of Biot-Savart as our brute force approach. So actually, let's do case number 2 first as a way to illustrate how we do the brute force method of figuring out magnetic field by applying the law of Biot-Savart. Okay, so let's draw that loop of wire one more time. Well, I didn't make it terribly symmetrical, but you get the idea. Okay. Let's see. If current flows in here, and then it goes around this way, and then comes back this way. How about right there, that little segment of wire, we could call it ds. And so if current flows to the right, ds is the vector quantity, and ds then is a vector that points in the direction in which the current flows through the segment ds. Okay? Now the distance from ds to the point in question is just this line, right? So there's r, and there's the vector. Oops, I guess I want to go this way. My goodness. Here, apologies. There's the vector r hat, and the magnetic field at this point is equal to mu naught over 4 pi I ds over r squared cross product with r hat. Now, here's the thing. What is the cross product of ds and r hat? What's the cross product of a vector ds pointing to the right and a vector r hat also pointing to the right? Well, when two vectors are parallel to one another, their cross product is 0. So all I'm really trying to express is that this part of the wire and this part of the wire, because they're in line with the radius, contribute nothing to the magnetic field at the center of the loop. So it's only this segment ds, or this segment ds, or this segment ds, right? Basically, any of this part of the loop that's going to contribute to the magnetic field at the center. So how about I draw again and we focus on one of those little segments of the wire. Okay, one more time. Okay, I think I drew it a little bit better this time. Current flows in that way and comes back out that way. And we'll focus on that little segment, call it ds. So it's a vector pointing to the right. There's the center of our loop. There's the distance r. And then there's the vector 1 unit long that we would call r hat. Now, the angle between r hat and ds points that way, r hat points that way, so it's 90 degrees. And so ds cross r hat in magnitude is just ds, the magnitude of ds multiplied by the magnitude of r hat, and then times the sine of the angle between them. But the angle between the two is 90, and sine of 90 is 1. And r hat has a magnitude of 1, so there's a 1 and a 1. So really, ds cross r hat in this case is just ds. Okay, so that's going to make things easy. Now I'm going to have to add the magnetic field from this segment ds. Now, this segment ds is a vector pointing that way, but then again, the r hat from here points this way. I don't think there's any segment of the wire for which ds and r hat will not be perpendicular to one another. ds points this way, r hat points this way, and so if they're all 90 degrees and r hat is a unit vector, then my goodness, if I want to find the overall magnetic field by summing up all the little bits of magnetism from each one of these segments of the wire called ds, then all I'm doing is summing up mu naught over 4 pi I ds cross r hat divided by r squared. But we found in this special case that ds cross r hat is just ds. And then the current I in this segment is the same as the current here, is the same as the current here. If every segment of the wire has the same current, then the current is a constant that can be pulled out of the integral. So this ends up being a very easy calculation, even though we're saying this is a brute force method. It's not too brutal, so to speak. So we have mu naught I over 4 pi times the integral of ds over r squared. Now, wait a minute. The distance from the center of the loop to the first element of the wire is the same as the distance to the next element and the next one. So even r is a constant. I probably should call it capital R. So b is equal to mu naught I over 4 pi capital R squared times the integral of ds. Now, as we work our way around any circle, the arc length is equal to the product of r and theta, right? S equals r theta. So ds is equal to r d theta. So if we pick any one of these little segments we call ds, it's approaching zero length, but not exactly zero, so it subtends a tiny little bit of angle we would call d theta, and the arc length of that ds is equal to the product of r and d theta. Okay, so we've taken the r squared out of the integral now, and we're just left with the integral of ds, which is the integral of r d theta, but that r can come out of the integral. This is easier than it looked to begin with, right? We just have mu naught I over 4 pi r times the integral of d theta. Now we got to figure out what are our limits of integration. So, well, the very first ds we have to account for is here, and then here, and then here. So as we go on and on, we're subtending more and more and more and more angle till we've gone a full 360 degrees. So in other words, in radians, we're going from 0 up to 2 pi. So we find that the magnetic field at the center of a loop is equal to mu naught I over 4 pi r times 2 pi. The pi cancels out, and lo and behold, we get our final answer. B is equal to mu naught I divided by 2r. So that's it. That's using the law of Biot-Savart to brute force our way into determining what's the magnetic field at the center of a loop. Now we could also ask, what if it doesn't go a full loop? What if we take the wire and wrap it around and around and around and around and decide to go like this? Now, once again, we can pretty easily argue that this segment of the wire and this segment of the wire don't contribute at all to the magnetic field at point P, because ds and r hat would be parallel in that case. Just to illustrate that one more time, let's pick a ds here, and if current flows in this way and comes around, then ds is a vector that points down in that direction. And let's see, that's r, so r hat is a vector 1 unit long pointing this way. Yeah, well, they're either parallel or anti-parallel, right? It's 180 degrees. ds points that way, r hat points that way, and so there's no cross product between the two. So we just have to pick any other ds around this loop, and I think all of our work's going to come out to be nearly the same as our first approach. We're going to say the magnetic field is the sum of all the little contributions to the magnetic field, which in turn is the sum of mu naught over 4 pi I times the vector ds cross r hat divided by r squared. So quite a few of these come out of the integral. Mu naught I 4 pi, we can change lowercase r to capital R, and then we're left with the integral of the cross product of ds and r hat. But for any one of these ds in this example, that ds points mostly to the right, r hat points down, the angle between them is 90. ds points that way, r hat points that way, the angle is 90. And r hat is just a vector of 1, so really this becomes mu naught I over 4 pi r squared, the integral of ds. And the integral of ds is the same as the integral of r d theta, and the r comes out of the integral and cancels with that. So we have b equals mu naught I over 4 pi r times the integral of d theta. And this time, it looks like I've made it, what, pi over 2, pi, 3 pi over 2, but I don't know, I could have said the wire bends here. We'll just say at some angle theta has been subtended. So we're going to integrate from 0 to theta. And so the magnetic field at the center of any curved loop, whether it's a complete circle or not, is mu naught I theta over 4 pi r. And once again, just to double check, if it happens to be a full loop, that means theta is 2 pi, and so mu naught I times 2 pi over 4 pi r becomes mu naught I over 2r, which is what we got in our first result. But a more general equation would be for any angle of a curved wire. The magnetic field at the center of curvature is mu naught I theta over 4 pi r, and let's be careful, make sure that theta has to be expressed in radians for this equation to be valid.